everyone. This is my little mock section, a recreation of a section that I'm doing for you guys since the video from section yesterday got messed up and didn't record properly or all the way. So I'm gonna try to get you all the information that you need for this quiz tomorrow. I'm gonna try to kind of work backwards and do what we covered in the most recent 2 lectures first, and then I'll go and do black holes and relativity, and then I'll go back and do the supernova type 1 and the neutron capture and how we create heavy elements. So I'm going to start off with the Milky Way and the structure of the Milky Way. So we live in the Milky Way galaxy, and from observations, we have figured out that it is a spiral galaxy. So looking down onto it, the galaxy's here. Now it looks like we've got this bar with these spiral arms coming out. Coming out around it. If we look at it from the side, so looking up this way at it, we see this central region called the bulge that's kind of in here. This is made up mostly of old stars, and they're all just kind of moving around in a sphere. And then we have what is called the disk. This is where the spiral arms are. This goes around on either side. Right, and then you have the spiral arms flat in this disk. So then around everything in a big sphere, we have what is called the stellar halo. And this is filled with old stars, the globular clusters. And they are not evenly placed throughout the stellar halo. A lot of these old stars come from other dwarf galaxies that were consumed by the Milky Way, and when they get into the outer edge of the Milky Way, the gravity from the Milky Way itself starts to kind of pull them apart, and as they revolve around the center, they leave these trails of stars. So you have these streams of stars going through the halo. The disk itself, where these spiral arms are, this is made up of gas and dust and young stars. So we have young stars in this disk because young stars are formed out of gas, right? Gas collapses down to make these stars. So all of these star-forming regions where young stars are born are all in this disk, in these spiral arms. And so that's why you have all these young stars there, because they're born there. Okay, so this is the basic structure of the luminous matter in the Milky Way. And then in the center here, in the very center of our galaxy, is a supermassive black hole. And it is about 4 times 10, not high Maxwell, to the 6 solar masses for this black hole. And it's not really doing anything. It's just kind of sitting there in the center of our galaxy. Stuff revolves around it, but it doesn't have a big accretion disk. It's not putting out jets or anything like that. It's mostly just kind of sitting there. As far as stars, there's about 3 times 10 to the 11 stars in the Milky Way. So one thing that you might want to do, if we know how many stars there are in a galaxy and how much gas and how much dust, is figure out what's the mass of our galaxy. And you would think to do that, you would just add up the mass of the stars and the mass of the gas and the mass of the dust, and you get the mass of our galaxy. Simple, right? It turns out it's not quite that simple. So there's a graph that you can draw called a rotation curve. And for our solar system, the rotation curve looks like this. So this is distance from the center, and this is speed, your orbital speed, how fast you're going around the center. So this tells us that planets closer in to the sun, right, with a smaller distance, so this would be, Mercury, are going to move faster than planets far away from the sun. Out here we've got, Neptune. Right? They have a farther distance, smaller speed. Shorter distance, higher speed. So this is what we expected to see when we started measuring the speeds of the stars going around the center of the galaxy. And instead, we got a plot that looked like this. Distance again. And this is really weird because this says that in general, it doesn't matter how far you are from the center of the galaxy, you're going to be going the same speed. And that didn't make sense with our understanding of the galaxy's structure and the mass. So one way you can think about this is we talked about escape velocity in class and in other parts of these sections. And escape velocity tells you, so this formula, the square root of 2gm over r, right? So as r goes up, as you get farther away from the center, your escape velocity is going to go down. So what should happen is these stars out here, they're going faster than what we would have measured the escape velocity to be based on our guess for the mass that we got by adding up the stars and the gas and the dust. So these stars should be flying out into space. They're going fast enough to escape the gravity of the galaxy. And that tells us, the fact that they're not doing that tells us that our escape velocity is wrong. So r, the distance, we've got measured pretty well. 2 is a number, g is a number, it's just a constant. So the only thing that we could have gotten wrong here is the mass. In order for these stars to still be bound to the galaxy, we have to have undercounted the mass by a lot. So that tells us that our galaxy has a lot more mass than just the mass of the gas and the dust and the stars added up. But we can't see it. We don't know where this mass is coming from. And so they came up with a name for it and called it dark matter. Dark matter is this extra mass that affects gravity, but light doesn't. Light just passes through it, basically. It doesn't absorb light. It doesn't reflect light. It doesn't create light. Like stars create light, gas absorbs light and then re-emits it. Dust can reflect light or absorb light. But dark matter doesn't do any of that. It doesn't really interact with light except through gravity. But it affects everything else through gravity. And we don't really know what it is. There's some theories, but there hasn't been like a really good explanation for what this is yet. But it increases the mass of our galaxy by a lot, to the point where if you add up all that stars and the gas and the dust, it's only about 30% of the total mass of our galaxy. So this missing mass, this extra 70%, this is dark matter. Okay? So that's how we know that there is a dark matter component to our galaxy, because this flat rotation curve, and these are called rotation curves. Right? It tells us that stars far away from the galaxy are going just as fast as, or far away from the center are going just as fast as stars close by. This is a flat curve. This flat rotation curve tells us that our mass has to be a lot more than we think it is, and that's our evidence for dark matter in the galaxy. Okay? So that is the other component to our galaxy that we can't see in this, and it is this big dark matter halo that we are embedded in, and throughout the whole galaxy there's dark matter. Okay, so originally we knew about our galaxy. We live in it, we could see the stars, but we didn't know if our galaxy was the whole universe, or were we just part of one of many galaxies. And in the early 1900s, they started getting better telescopes and being able to take better pictures of space, and they started seeing other galaxies. Although at the time, they didn't know, were these other galaxies, or were these just small things that kind of looked like galaxies embedded within our own galaxy? So there was what they called the Great Debate. And the question that they were debating was, are these things that we're seeing in these pictures, are they small things embedded in our own galaxy? Are they spirals in our own galaxy? Or are they something much farther away, just as big as our own galaxy? Are we just one galaxy of many that are lots of them just as big as our galaxy, some of them bigger, some of them smaller? Or is the whole universe our galaxy and everything else is just inside of it? And the answer that they came up with, or that they figured out, is that these are not inside of our galaxy. We are just one galaxy out of many. And so, Maxwell, stop it. Sorry, my cat is playing noisily. So they figured out that we are just one galaxy out of many. And galaxies tend to group up. So we are in a group of galaxies called the local group. And the three largest in the local group are Andromeda, the Milky Way, and another galaxy called the Triangulum Galaxy, or M33. And then there's about 100 or a couple hundred dwarf galaxies. These are like little small mini galaxies, and a lot of them rotate around the bigger spiral galaxies. So we have a lot of these dwarf galaxies that go around the Milky Way. The two biggest are called the Magellanic Clouds, the large and small Magellanic Clouds. Then there's a bunch of other ones. Some of them are in the process of being broken up by these tidal forces and leaving these streams behind in the halo. And some of them are still able to just go around and retain their shape. All right, so we are in the local group, which has a couple hundred galaxies. Most of them are dwarf galaxies. And then the local group is part of, above groups, there's clusters. And then a bunch of clusters together make up a supercluster. So we are part of the Virgo supercluster. And then you get bigger and bigger and bigger structure. And when you pull back, and look at the structure of all the galaxies, it looks almost like a close-up of a sponge. Right, you have lots of interconnected threads and holes all through it. And that is the kind of large-scale structure of the universe. But just for our local structure, you've got a couple hundred. We're sort of gravitationally bound together, and most of them are dwarf galaxies. So we are one of the biggest in the local group. We're the second biggest in the local group here in the Milky Way. Okay, so that is our galaxy and a little bit about some other galaxies. One thing to know about Galaxies is that while the Milky Way is one of the largest in the local group, there are other galaxies that are much, much, much larger. There are galaxies that are much, much, much smaller. So there's just a huge range in galactic size, and we are not at the top of that range. There are plenty of galaxies that are just dwarf our galaxy in size and in mass. Okay, so looking at a couple of the homework problems. Get out of the way. Number 10 says, which of the following are components of the Milky Way galaxy? The first one is a rotating disk containing stars, gas, and dust. So that's true, right? That's this disk right here. It has the spiral arms inside of it, and it's got a bunch of stars and gas and dust, and the stars are made out of this gas and dust. So then a 4 times 10 to the 6 solar mass black hole at the center. That's true. That's this guy here in the center. An extended low-density spherical halo with stars and globular clusters. That's true. That's this out here. It's not very dense compared to the disk or the bulge, but it's got stars and then these globular clusters, which are these gravitationally bound groups of stars going through it. And then a bulge of gas and young stars. So there is a bulge, but the bulge mostly has old stars in it, not young stars. And it doesn't really have gas in it. So that part is not true. 11 says, what is the evidence for a dark matter component of the galaxy? And this is this rotation curve here, right? So objects at a large radius from the center of the galaxy have a much greater speed than we think they would. If there weren't any dark matter, it would look like this, and they would be going very slowly. But they're going a lot faster than they think we would. So we know that the mass of the galaxy is a lot greater than it looks like. So this rotation curve tells us that stuff at a high radius from the center is going faster than we would expect. So there's more mass in the galaxy than we initially calculated. 12 is, what was the subject of the 1920 Great Debate between Herbert Curtis and Harlow Shapley? This is is our galaxy the whole universe, and are other galaxies just inside of our galaxy? Or are we just one of many, many galaxies? And some of them are as big or much bigger than our galaxy. And are we all part of a larger universe? And the answer to that is that we are part of a larger universe, and we are just one of many galaxies. So 15 says the local group of galaxies contains, this is a true or false, several thousand galaxies. That's false. Several galaxies of comparable size to the Milky Way and a few hundred dwarf galaxies. So that's true. We've got a couple that are about Milky Way size, so that's Milky Way, Andromeda, and Triangulum. And then a couple hundred dwarf galaxies. So a few hundred galaxies, including some much larger than the Milky Way, that is not true. The Milky Way is the second largest, and they're all on the same kind of comparable size. And then a mix of large and smaller galaxies along with several energetic QSOs, that's quasi-stellar objects, and that is not true. So the discovery that our Milky Way galaxy is one of billions of galaxies in a very large universe was made by, they discovered this. This happened when they started taking these pictures and got better idea of, started seeing other galaxies. This happened in the 1920s about when we discovered that we were one of many galaxies. And so the answer to this is C. Astronomers from the early 1900s who first used photographic plates to make images of the sky to much fainter levels than was previously possible. So the other answer is the first A is astronomers in ancient times in many different cultures. So this part is not true. Most ancient cultures thought that the Earth was the center of the whole universe, right? And the sun and all the planets revolved around the Earth. And then B is Galileo, when he used the first telescope to view the sky. So Galileo figured out that the Earth revolved and all the planets revolved around the sun, but he couldn't see other galaxies. And he couldn't really see much about the structure of even our galaxy. He kind of focused on our solar system. And then, so C is correct, and then D, astronomers in the last decade using the Hubble Space Telescope. Well, they figured it out in the 1920s, so it didn't take until the last decade, but they have been able to see more and more and more and more galaxies with Hubble, and we can see them in more and more detail. So, I said before that our black hole in the center of our galaxy isn't doing much. So how do we know that it is there? Well, when we look at stars that are close to the black hole, we have the black hole here, they're orbiting it, right? You have stars that are orbiting something here, and everything's orbiting around the same point. And so we know something has to be there, right? If you're orbiting around something, then that thing has some sort of pull on you, some sort of gravitational pull in the case of these orbits. But we don't see anything there, right? There's no giant star there to have them orbit around. So that's how we know that it's a black hole. We know that it has a really strong gravitational pull, and it's really small because these orbits are really fast and they get really close in. So this is how we know we have one in our galaxy. But not all black holes in the center of galaxies are just hanging out there. A lot of them are actually sucking in matter. They're accreting. And what happens when a black hole is pulling gas in is you have the black hole and gas comes in and it spirals around before it falls in. And so you have this disk of super hot gas that surrounds this black hole in the center, right? So as this gas falls in and spirals around, it gets really dense and the pressure goes up and the temperature goes up. We learned at the beginning of this class that things that are hot emit light, right? We have these spectra from things that are hot. So these heat up. This matter that's in this accretion disk around this black hole heats up and it emits X-rays and other light. And so they emit stuff. And then also, if we look at it from the side, this little accretion disk, and you have the black hole in the middle, sometimes you get these big jets of matter coming out on either side. And we're not totally sure why this happens. It's probably from magnetic forces in this accretion disk. Excuse me. But it's important to note that these are not coming from the black hole itself, right? Nothing can escape from the black hole itself. These are coming from the area around the black hole where this gas gets wound up really tightly and has a lot of pressure and it's moving really fast and gets really hot. And so that emits these X-rays that shoots out these jets. But anything that gets to the black hole itself gets sucked inside and doesn't shoot out no light comes out of the black hole itself. Okay? So these couple more questions. Question 13 says, what is believed to be the source of energy for QSOs and active galactic nuclei radius? Right, so if a galaxy has a black hole that is accreting or shooting out these jets, then we call it a active galactic nucleus. They used to call them QSOs, quasi-stellar objects, because right, these are glowing, they're giving off light, but there's no star there. So the source of energy for these QSOs and active galactic nucleus, the first one is material being heated as it's falling into a supermassive black hole, and that is true. This material falls in, it gets heated up. Intense bursts of star formation, that's not happening, that's not true. Series of supernova 2 explosions, that's not happening, that's not true. And runaway thermonuclear reactions in the center of the galaxies, that is also not true. So the only one of these four that is true is this first one. It is this material that gets heated up as it falls into the supermassive black hole. And then 14, which of the following are observations that have led us to believe there is a supermassive black hole at the center of the galaxy? The first one is gas clouds being ejected from the center of the galaxy at escape velocity. That is not true. Not our galaxy. There's no gas clouds being ejected from ours. It's basically just sitting there. Orbits of stars near the center of the galaxy, that is true. That's how we know that there's something really massive there. That's how we can measure the mass, by looking at these orbits. The regular disappearance of stars near the center of the galaxy, that is not true. These stars are not getting close enough to actually get eaten up by the black hole. And then extremely energetic photons streaming from the center of the galaxy, that is also not true. Like I said, it's basically just sitting there as a black hole, and these stars are orbiting around it. So the only one of those is the second one. Okay, so that is our galaxy and some other galaxies. And then I'm going to talk a bit about cosmology and expansion. But first, I need to go a little bit, and try to make this brief, go into the Doppler shift and how we know how fast things are moving. So it's pretty easy to measure how fast something is moving, like transverse to you, right? I can look at something now, and a little while later I can measure it when it's here, and I can say, okay, it moved this far in this amount of time, and I can calculate the speed from that. But if something is moving towards or away from you, you can't really do that, right? You can't tell how far it's moved towards you or away from you, especially if it's really far. It's not changing size or anything. So we have to have a different method for measuring how fast something is moving towards us or away from us. And what we use is something called the Doppler shift. So the way that this works is when you have something that is emitting waves, they can be electromagnetic waves, they can be sound waves, they can be, you drop something, in a pond and it creates water waves. It just has to be emitting waves constantly, right? So if it's just sitting there, this guy's here and he's emitting waves, right? He sends a wave out and it moves outwards. And every time it gets to a certain distance, he sends a new wave out. So this one was sent out first, right? It started here and it moved outwards. And when this one got to this spot, this next one got emitted, right? So this one was first, second, third, fourth. And they're all moving outwards, right? So that's what happens if you've got this guy in the middle just standing still. But what if he's moving? So he's going to send his first one out. And it's going to go out in a circle based on his original spot. But then he moves, and by the time he sends out this second wave, he's right here. So this one's going to go out in a circle based on this new spot. Then he moves here, and he sends out another one. And this one's going to go out in a circle based on this new spot. And then he moves here. He sent out his last one. And it's going to go out in a circle based on this new spot. So I'm going to compare the wavelength, which is the distance between these peaks, right? So in this one, the way it should be is that the distance for each of these is the same, no matter which direction. All of these distances between the two peaks are going to be the same. But when you have this one with a moving source, you can see that if you're measuring it this direction, these distances are shorter than these ones. Right? So on this side, when it's not moving, this distance here is the same as this between these two. But for this guy, this distance here is longer than this one. So this guy is moving in this direction. So if you are standing here with your eye looking at this, you're going to measure this wavelength. And you're going to measure the same wavelength no matter which direction you're looking at it, right? If you're looking at it from this direction, you're going to measure the same wavelength as if you're looking at it from this direction. But this guy over here, if he's looking at it from this direction, he's going to measure a long wavelength. And this one over here is going to measure a short wavelength. This one is going to be longer than this wavelength. This is going to be shorter than this wavelength. So what that means is that if an object is moving towards you and it's emitting light or any sort of wave, you're going to measure a wavelength that is shorter than the rest wavelength of that wave, or what the wavelength would be if nobody was moving. And if it's moving away from you, right, you're here and it's moving away, then you're going to measure a wavelength that is longer than this rest wavelength, right? So if it's moving towards you, you get shorter wavelength, and that is more blue. If it's moving away, right, you get longer wavelength, and it's more red. So this is called red shift, and this is blue shift. So if I say that something is red shifted, that means that it's moving away from me. Something is blue shifted is moving towards me. Okay? Another way to think about this is in terms of frequency. So frequency is like if you're walking, you want to count how many peaks go by you. Right? So if you're just standing still here, these peaks are going to go by you at the same frequency as they were emitted. But if you're walking towards this source, you're going to count these peaks as going by you faster than if you were standing still, right? If you and something else are walking towards each other, you're going to get to each other quicker than if you were just standing still and they're walking towards you. So you're walking towards this wave coming at you, and it's going to happen. You're going to pass by you quicker and more often than if you were just standing still. So you get an increase in frequency, which is the same as a shorter wavelength. Right? So you walking towards something that's still is the same thing as something moving towards you and you're standing still, right? What matters is, are you guys going together or are you moving apart, right? So if you're moving towards it, then that's the same as it moving towards you. Okay, so this is called the Doppler shift. Something gets red shifted or blue shifted. And why is this important? Because this is how we can tell velocities. So, we talked about in the previous sections about how every different element has a special pattern in its emission line spectrum, right? This comes from when you have these different orbital energy levels, and when an electron is in a high energy orbital level, it jumps down to a lower one, and it releases a photon. And the photon wavelength depends on how far it had to jump. And every different type of atom, every different element, has a different pattern for how far apart these levels are spaced. So you get different pattern of wavelengths for different elements. So we, in a lab, can look at an element with the spectrometer and find out its pattern, right? So, and it looks like you have, wavelength and intensity. So how much, right? And wavelength, you've got, purple down here, blue, it goes in the rainbow, right? All the way over to red over here. Here's the green area, yellow, orange, and red. So if I have an atom, we'll call him hydrogen. This is not really the spectrum of hydrogen, but, let's pretend. And hydrogen has one line right here in this blue, and another one here in the orange. So he has one line in the blue and one line here in this orange. So if this hydrogen atom is moving towards me, then his wavelength is going to get redshifted. And when I measure his wavelength, everything's going to be moved over. So this blue line is now going to be in the purple area, and the orange one got moved into yellow. But the pattern stayed the same, right? The distance between this one and this one is the same as the distance between this one and this one. So, I guess we can draw this out a little further. Right. They should have the same distance. So when we look at something and we say, oh, this pattern, these two lines with this exact spacing, we see something that looks like the pattern, but it's not where it should be. We know that this pattern has been shifted, right? So if this were moving away from us, right, they all move towards the blue side. If this were red shifted, then this blue would go into the green section, and the orange would move into the red. Right? But this spacing and the pattern would stay the same. And so we don't look for specifically where the lines are when we look at something. We look for the pattern. Say, okay, I recognize this is the hydrogen pattern. Now, how far away is it from where it's supposed to be? And that difference, how far away from it where it's supposed to be, that tells us how much it's been shifted. And how much has been shifted tells us how fast it's moving towards or away from us, right? If it gets shifted towards this side, if these move this way, that's a blue shift. If these move this way, that's a red shift. Blue shift is moving towards us, red shift is moving away from us, right? So that is how we tell velocities. shift from this Doppler shift. Okay, so once we figured all this out, we could measure velocities of stuff, of other galaxies even. And in the early 1900s, so like 1912 to 1915, this guy, Vesto Slipher, started measuring all of the velocities of all the different galaxies that we were seeing. And he learned that almost all of the galaxies are moving away from us, right? There's a couple, the ones in our local group that are bound to us gravitationally, that are moving towards us, but almost all the galaxies are moving away from us. And then Edwin Hubble went and he compared how fast they're moving away to how far away they are. And he came up with a plot that looks like, where's my marker? This. And this is distance. And this is recession velocity. So this is how fast they're moving away from us. And except for a couple things close by us, almost all the galaxies are moving away from us. And the farther away from us they are, the faster they're moving away. Right? So they're farther away, they're moving away faster. And the only way for something like this to make sense is to assume that everything everywhere is expanding. So the way that this kind of works is, my markers. So he showed this in class. If you've got a row of galaxies and the space between them expands, and at the next minute they are, the next time they get measured, they're spaced out like this. And then the next time, they're spaced out like this. There's kind of two things that you can see from something like this, right? First of all, say we're this center galaxy, right? And we go from this time to this time to this time. And as time passes, all of these other galaxies get farther away from us, right? This one started off really close. This one started off close. They're farther away. This one was closer to us than it is here, right? Everything gets farther away from us. So we might think, okay, that tells us that we're in the middle. But that's not actually true. Because if you look at this galaxy out here, he also sees the same thing. As he goes here and here, everything is moving away from him too, right? This guy here is farther away from him. This guy is farther away from him. This one is farther away from him. This one is farther away from him. Every one of these galaxies is farther away from this one than when it started. See, for this guy here, every one of these galaxies is farther away than when they started. So that means if you have a uniform expansion, everything is expanding in the same way, all of the spaces between these galaxies are growing in the same way, then for every one of these galaxies, it's going to look like everything is moving away from them, which is just what we see, basically. Everything is moving away from us. So that fits. The other important part is that things that are farther are moving away faster, right? And we see that from here, right? So at the distance, you know, as we go from here to this time, this distance grows to this distance. In the same time, this distance grows to this distance, right? So this is a bigger increase than this. So this guy has to be moving faster to move a farther distance in the same time, right? This guy only moved a little bit. This guy moved a lot. So this one has to be moving faster than this one to move that bigger distance in the same amount of time, right? And now this one moves to here, but this one's moved all the way out here. So the farther away you are, the faster you're moving. And it's the same thing if we look at this guy, right? If we're this one next to him moved this distance, but this one over here moved all the way out here. And that's a bigger distance, so it has to be moving faster. So one thing that is kind of confusing about this is that it's not the galaxies that are moving through space, right? They are, but that's not what's happening. It's not that the ones out here are moving faster through space. It's that the space between them is getting bigger, and the space between every galaxy is getting bigger. So this galaxy gets this stretch, right? But this galaxy gets this stretch and this stretch. So that's why it's moving faster. It has two stretches. So to kind of demonstrate this idea of the space expanding, but the galaxy's not moving through it, I've got this little rubber band, right? And I stuck two like pins through it. And so these pins are my galaxies in space, or in space-time. And as I stretch this rubber band, these galaxies get farther away from each other, right? But they don't move on the rubber band. They're in the same spot on the rubber band. They're stuck through it. So as the distance between them gets bigger or smaller, they're not moving across this rubber band, right? This guy is not moving to a different part of the rubber band. He's staying where he is, but the rubber band itself is stretching. So that's what's happening to these galaxies. The space between them is stretching. But they aren't necessarily moving to a different spot in space. Right? So this is expansion of space-time. It's this rubber band stretching. And if you have another galaxy on here, right, then that would be stretched also. Would stay where it was, but it would get the stretch between it and these guys. So another way to think about it is like a balloon. If you put a bunch of dots on a balloon or glue coins to a balloon and then blow that balloon up, each coin is going to stay, you know, in the same spot that it was glued to, but the balloon itself, that fabric of space-time, is stretching between the coins. So all of them are going to get farther away from each other than when they started off. And I have a little like animation demo that I'm going to link down in the description of this video that you can look at to see an example of this, and then also kind of one for the Doppler shift that you guys can look at to see if that helps you at all. Another way to think about it is that I've seen is like if you're baking a raisin bread, and when you put it in the oven first, right, you've got this ball of dough and it's got these raisins and they're all close together. And then you put it in the oven and the dough itself expands, right? And as that happens, all of the raisins get farther and farther away from each other, but they don't move through the dough. It's the dough that is expanding, right? So it's the space between them that is expanding. They aren't moving through the space. Okay, I know it's kind of a weird concept, but again, it's like this rubber band, right? These are staying in the same spot on the rubber band, but they're getting farther apart because the rubber band is being stretched between them. Okay, and so the homework questions. 17 says Vesto Slipher obtained spectra of galaxies during the period 1912 to 1917 and made what remarkable discovery? This is that the vast majority of galaxies are moving away from us, right? And then 18 says the vast majority of galaxies are moving away from the galaxy. There's a linear relation between the recession velocity and the distance to the galaxy. That's this plot here, right? This is a line, distance and recession velocity. The interpretation of this is which of the following? So is it that the galaxy is at the center of the universe? That is not true, right? Because any of these galaxies would see everything moving away from them. Space-time is uniformly expanding. That's what we get from this, right? All of these spaces are getting bigger at the same rate. Galaxies were ejected by the Big Bang. Galaxies formed after the Big Bang. So that's not true. Cepheid variable stars have been ejected from their host galaxies. That would have to be all of these Cepheids that we were measuring got ejected, and that doesn't really make any sense. Okay, so for this one, it's that space-time is uniformly expanding. So if I turn this around and say, how do we know space-time is uniformly expanding? Then we would look at this and say, okay, we know it's expanding because everything is moving away from us, and the farther away it is, the faster it moves. Okay? So that is space-time expansion and other galaxies and our galaxy. And that is it for this kind of section of the homework. And I'm going to do another video on relativity and black holes, and then another video on supernova and supernova type 1 and how we get heavy elements. So please, if you guys have questions, send me an email. And then I hope that this is helpful.